We are on FRQ topic 5. This is the topic on differential equations. You see the most recent years that we've seen these types of questions on the AP exam. So you see that, not every year. I see 2022 was missed, 2018 was missed, but a lot of years. So this is another one of those common ones. Differential equations is also an AB topic, so when you see one of these questions, it will likely be common on the AB exam as well as the BC exam. Okay, remember our mantra for solving a differential equations, STI, separate then integrate. You are finding a solution, you're finding the y value. They're given y prime, we want to find y. Alright, dy dx, you find y. Alright, so that's what we're doing here. The difference is, a lot of times there will be y's over there within the dy dx expression, there will be y's over there. So you have to separate first, then integrate. Separate, then integrate. Okay. So carefully separate, use good algebra, integrate both sides. Lots of times AP will be seeing if you know how to integrate. If it is a BC only, if this is not common to AB, then you will likely have to use by parts, partial fraction decomposition, etc. Okay? Don't forget the plus C. Then you're going to find C using the initial condition that they give you. Be sure to say what you're doing. And very lastly, solve for y. Get y by itself. You are solving the differential equation. Use good algebra to find y. Sometimes on these problems, it also involves a slope field. Okay? You will either sketch a slope field or sketch a curve through a given slope field. Okay? Another type of question is finding the equation of a tangent line, using the equation of a tangent line sometimes to find a value of your function. Oftentimes in here you'll have to find a second derivative. So they give you dy dx, you find the second derivative. Make sure that you're using implicit differentiation. If there are y's over there, you have to multiply by dy dx when you take its derivative. You'll have to use the second derivative. So to determine concavity, to determine if a tangent line is an over or an underestimate, yeah, things like that. Okay. Euler's method, another common thing to see here. You're given a dy dx, so you can use Euler's method. Okay. And let's talk about logistic differential equations. So a logistic differential equation is a specific type of differential equation in this form. Okay, remember, 2 p's over here. So 3 p's altogether, Mrs. Murray, right? All right, so that's the form of a logistic differential equation. Recognize it. Okay. That L value, when it's in this form, that L is the carrying capacity or long-term behavior. It's the limit as P goes to L, it's the limit as time goes to infinity of P, and that's L. Okay? All right, dp dt is largest when P is half of L. The population is growing the fastest. I'm going to fix this. That should be fastest when P is equal to 1/2 L. There are 3 types of solution curves depending on the population at time 0, the initial population. This by far is the most common. We're concave up until P is equal to 1/2 L and then concave down after P is equal to 1/2 L. But P is always increasing. So dp dt is always positive. This is the second one, and this is the third one. Remember, if you put too many fish into a pond, what's going to happen to the fish? They're going to die, right? So, and it's a quick death, right? All right. We don't know anything about time. I don't know where that came from, but I'll get rid of that on your paper. Don't know anything about time. Okay. Alrighty, so let's take a look at some problems now. Okay, let's start by taking a look at the problem from 2017. Put that underneath here, get it out of my way. Okay, 2017. Global average was 3.1. That's pretty low. So kids had a hard time with it this year. At time 0, a boiled potato is taken from a pot on a stove and left to cool. The internal temperature is 91 degrees at time 0. They're giving us an initial condition. When time is 0, the temperature is 91 degrees. The internal temperature of the potato is greater than 27 degrees for all times. I don't know why they're telling me that. That's a weird piece of information. So I will try not to forget it's there. Because I guarantee when they give me an odd piece of information like that, I'm going to need to use it at some point. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies this differential equation. I look at it and I see that it's separable. I'm guessing we're going to have to separate and integrate. Okay. Part A. Write an equation for the line tangent to the graph of h at time 0. Use the equation to approximate the internal temperature of the potato at time 3. Point and slope. The point. They tell me what the time is for my line, for my tangent line. The point is when time is 0. And at time 0, what is the temperature? 91. Slope. They give me a way to find the slope, right? So at time 0, the slope will be, I'm not putting 0 in for h, I'm putting 91 in for h. The slope will be negative 1/4 times 91 minus 27. Okay? Now, I could work that out. If I want to, I could work that out. Or you can just leave it like that. If you wanted to, you could call that something like maybe m for slope, right? Something like that. Or just leave it like that. So the equation will be y minus the y coordinate of our point is equal to the slope. I think I'm just going to write it out. Times x minus the x coordinate of our point. Remember that x in this problem is time. Y in this problem is the temperature, right? So they're asking us to use this to approximate the temperature at time 3. So h at time 3 is approximately equal to, I'm bringing the 91 over, rewriting everything else, and I'm putting 3 in for x. And that is the approximation for the temperature at time 3. Part B. Use the second derivative to determine whether that tangent line approximation is an over or an underestimate. Okay, so first I need to find the second derivative. I'm going to write the first derivative, leaving a space because I'm about to take the derivative of both sides with respect to t, because I'm getting the second derivative with respect to t. So I will have the second derivative of h with respect to t. Okay, oops, I'll get to where you can see it. Okay. All right. What's the derivative of this? If we distributed, I would have negative 1/4 h plus 27 over 4. The derivative of negative 1/4 h is negative 1/4 dh dt. The derivative of that constant is just 0. So this is the second derivative. Now, I know what dh dt is. dh dt is negative 1/4 times h minus 27. Now, in the problem, they told me that h was greater than 27. Remember the odd piece of information? Well, here's where we use it. H is always greater than 27 degrees. So that means this is always positive. That means this thing is always positive. So the second derivative is always positive. Therefore, a tangent line approximation yields, and okay, we're concave up, right? We're concave up. A tangent line will be below the curve. So it yields an underestimate of the actual value. Okay? Part C. Oh, there's only 3 parts. I think I'm going to put part C over here because there's only 3 parts here. Alrighty, part C. For time greater than 0, an alternate model of the internal temperature of the potato is this function g that satisfies this differential equation. G is still in degrees Celsius, G of 0 is still 91. Find an expression for G of t. So here's our separate and integrate. And then we need to find the exact internal temperature at time 3 after we find G. Okay, so here's dg dt. Okay, I'm going to carefully separate and then I will integrate. So I'm going to divide both sides by this g minus 27 to the 2/3. That will make it g minus 27 to the negative 2/3 dg. And then I'm going to multiply both sides by the dt. I still have that negative over here, so negative dt. So I have separated. Now I'm going to integrate. Alright, we can do a u sub here, but u will just be, du will just be a dg. So I'm treating this like a u, but I'm not actually going to do a u sub. So I will have u to the, I'm doing the power rule, add 1 to the power, divide by your new power, is equal to negative t plus c. Remember, we combined the constant on the left with the constant on the right and just wrote it as a singular constant. I'm going to divide both sides by 3. When I divide the c by 3, I just get another constant. And now I'm going to find c. So I know that g of 0 is 91. I'm saying what I'm doing. G of 0 is 91 will give me, 91 will give me 91 minus 27 to the 1/3 is equal to 0 plus c. So that's c now. And now I can write, now I have to come back and solve g, right? Solve for g. Okay, since I've already said the value of c, I'm just going to leave this as a c since I've already given the value of c. I'm going to cube both sides. and then add 27. Okay, so I separated, integrated, found C, and then solved for G. And now lastly, they tell me to put 3 in for T. So I will do that and call it good. All right. Scoring on this problem. 1 point, part A. 1 point was for the slope at time 0. 1 point was for the tangent line equation. 1 point was for the approximation. 3 points. Thought that would only be worth two, but it was worth 3 that year. Part B. Part B, I would think would be worth 2 points, but it was only worth 1 point. 1.4, underestimate with reason. And part C. C here was worth 5 points. 1 point was separation of variables. 1 point was for the antiderivatives. 1 point was for the constant of integration and uses the initial condition to find C. One point was for the equation with G and T. And then I'll squeeze it in here. 1 point was for G of T and G of 3. So 5 points for that one. Alrighty. Next one we're going to do together is the problem from 2019. Okay. KHS's average was a 4.0. So not terrible, but not fantastic. A cylindrical barrel with a diameter of 2 feet. If the diameter is 2 feet, what's the radius? 1 foot. Okay. Contains collected rainwater. The water drains out through a valve at the bottom of the barrel. The rate of change of the height, so the H is going down because water is draining out. Okay. The rate of change of the height is modeled by this differential equation. H is in feet, T is in seconds, and they give me the formula for the volume of a cylinder. Part A, find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. I need to remember to do this. I already know what the units will be because H is in feet, T is in seconds. I'm finding the rate of change of the volume, so I'm finding dV dt. I know it's going to be units of volume divided by units of T. Feet cubed per second. That's going to be my units. I already know the units. I just need to remember to put them down here in my problem. In my response, I mean. Okay. So they give me V. But we very nicely are given a cylinder. And we are given the radius of the cylinder. And this cylinder's radius is never changing. The cylinder is not changing its radius. So R is always 1. So V is always pi h. I'm going to come in and take the derivative of both sides with respect to t because they asked me to. So dv dt is equal to the derivative of this with respect to t. Well, the derivative of pi h is pi, and then we need to multiply by dh dt because of chain rule, implicit differentiation. Okay, so that is dv dt, and now we need it when h is 4. I know what dh dt is. dh dt is negative 1/10 square root of h. So when h is 4, this will be pi times negative 1/10 square root of 4 feet cubed per second. Little related rates problem. Okay. Part B. When the height of the water is 3 feet, is the rate of change of the height of the water, is the rate of change of the height, that is dh dt, is it increasing or decreasing? Is this increasing or decreasing? Well, to find out if this is increasing or decreasing, I need its derivative. So I'm going to be taking the derivative of dh dt, plugging in 3 for h, and asking myself, is that positive or negative? So, little second derivative again. dh dt is negative 1/10 square root of h. I'm going to take the derivative of both sides with respect to t. To get the second derivative. So the derivative of this is h to the 1/2. So 1/2, that'll be negative 120. H to the negative 1/2, subtract 1 from the power, dh dt. Okay, that is negative 1 over 20 square root of h times dh dt, which is negative 1/10 square root of h. These square root of h's cancel each other out. This thing is always positive. Always positive. So when the height is 3, or when the height is 4 or 5 or 2 or 1/2 or whatever, the second derivative is always positive. So the first derivative is always increasing. So dh dt is increasing at h equals 3. Okay? I might put a little therefore symbol there. Excuse me. Part C. At time 0, the height of the water is 5 feet. Use separation of variables to find an expression of h in terms of t. Separate and integrate. Use this to find c. Alrighty. Part C. I take my dh dt. I'm going to separate and integrate. So I'm going to divide both sides by h to the 1/2. That will be h to the negative 1/2. Multiply both sides by the dt. Like that. I have separated. Now I integrate. Add 1 to the power, divide by new power. Negative 1/10 t plus c. I'm going to multiply both sides by 1/2. Multiplying both sides by 1/2. Okay. Now I'm going to use my initial condition to find C. So when time is 0, h is 5. So I have the square root of 5 is equal to C. H to the 1/2 is negative 1 over 20t plus square root of 5. Last step, solve for h. Square both sides. Okay, do I have to do anything with this? No, I did not. So I'm done. That's it. Let's see how much each of these was worth. Part A. Part A, 1 point for, I'm looking at the last problem. 1 point was for dv dt is equal to pi dh dt. So that step, that very first step, 1 point for that. 1 point for the answer with units. Two points for part A. Part B. Part B, 1 point for, so 1 point was for this step right here. Just taking the derivative with respect to h of dh dt. So this is how they wrote that. Okay, so just this piece. And then 1 point for the chain rule part, finding the entire second derivative. And then 1 point for your answer. With explanation. In other words, you had to have earned the first 2 points to get that last point. So 3 points for part B, leaving 4 points for part C. For part C, 1 point for separation of variables. 1 point for the antiderivatives. 1 point for the constant of integration. And uses initial condition to find that C. 1 point for the answer. The answer, to get the answer, you had to have done everything in front. It had to be the correct answer, not just solving for any h, but the correct h. Okay, in every one of these where you're solving a differential equation, if you do not separate, you are not eligible for any of the remaining points. Okay? You have to separate to be eligible for any of the points. Okay? Alrighty, that's it for differential equations.